Good. Now let me get back into the rhythm. I chose the title here, Choose Optimism, and that's because really at heart I am an optimist. However, I think it's important that as a field we recognize that we're starting to actually get a bit of an anti-tech trend out there. If you're sitting in Silicon Valley or you're up here in Seattle, kind of Cloud Valley, you don't really feel it as much. But realistically, we've had sort of, if you think about it, the press that you're seeing based on whether it's security breaches, privacy breaches, and in many ways, angst about AI and ML, the public anxiety about tech is building up, and there's starting to sort of be a narrative that's a bit of an anti-tech narrative. I think it's important that we be aware of it. It's important that we sort of confront it, and it's important that we sort of present, I think, the optimistic side, because the press tends to pick up the pessimistic side. Now, GeekWire would never do that, but the sort of mainstream press, I think, does tend to go down that path. Now, this isn't anything new. This is here. I'll just speak loudly. There we go. See? It works. So this is one of my favorite quotes, and it's a very old one about dealing with, in this case, it was a bad attack of economic pessimism. I'm going to get to the rest of the quote, but what I want you to realize is with respect to AI and ML, a lot of the concern has to do with its concerns that, hey, the computers are going to take all the jobs, and also concerns that we don't necessarily really understand what a lot of these machine learning systems are doing. And that's something that Carlos sort of hinted at. He talked about concerns about the data. I think the problems actually even go deeper than that. When folks get in a car or they get in an airplane, et cetera, they don't, how many of you understand really exactly how a jet engine works? Right, but we do get in the plane. And the reason is that we have confidence that the engineers that designed that did understand how it works. And if we start foisting technologies on the world, particularly AI and ML technologies, where we, the engineers, and we don't understand how it works, we're sort of breaking our deal with society. So I think it is important that we get ahead of some of these things, both in terms of the concerns about jobs and some of the concerns about, do we really understand how the stuff works, and are we deploying stuff that we know how it works, and is it under control? So those are the two main topics, the two main threads I'm going to cover. Now back to that favorite quote, the continuation of it is that, I think all that pessimism is really missing that there's great things happening, right? We have great opportunities with AI and ML to do good things for the world, to improve productivity, to improve people's health, people's social well-being, many other aspects. This quote in particular is quite an old one. It comes from Keynes circa 1930. So they were dealing at the time with sort of, one of a number of infusions of technology into society. Okay? Looking for the other microphone. Oh, it's right here. Okay. One microphone. Just when I was talking about abundance. But this is the history as new technologies come along. These two charts illustrate it with sort of two cases, innovation of the cotton gin and auto manufacturing, high volume manufacturing into the auto sector. These are just two of many historical cases, and the pattern's pretty much the same, right? Innovation comes in, it improves productivity growth. Notice the innovation with, was high volume manufacturing for cars. It wasn't really cars, but figuring out how to make them in high volume. So that innovation, which could be applied to many things, came into that sector. It drove down costs. Now, initially, when it first drives down costs, it's still the case that only the people that can really afford that expensive, desirable thing can continue to afford it. But as it continues to drive down the costs, now large fraction of the population can afford these things, and that drives demand, and now you've got that desirable thing becoming abundant. And that demand creates a whole pile more jobs and opportunities. So this is the pattern. We've seen it over and over. It's particularly fierce with technologies like electricity, like the internet, and now like machine learning, where these are going to affect large swaths of the economy, right? Many, many different areas are going to be affected. And these things do create dislocation. So on the long term, they create more jobs. That's the known pattern. And on the other hand, in the near term, they create dislocation, right? People lose their current jobs and have to find new jobs, and they have to learn new skills in order to do that. And to be honest, in the past, we've never been good at this retraining thing. So there's no good past track record of actually making retraining work so that those people can find new jobs and actually, kind of get back on their feet. So this is a serious social problem. Now, there is something that's different. People always say, but maybe it'll be different this time, right? Maybe there won't be more jobs in the end. Maybe it'll be different. I think the thing that's different, though, is that actually this time, and sorry, I'm going to skip through this chart just because we got a little bit of a late start, but it's just more quotes. This time, we actually have a change in demographics. So it's not a difference that's technical, it's a change in demographics. And it's not just in the US, it's not just in Europe, it's in places like China, Japan, and people are now starting to realize, even in India and Southeast Asia, the demographics are shifting. So in those past transitions, you actually had a surplus of workers. Something that we're facing, certainly in the developed economies, but as I said, also in many other economies, is we're actually going to have a shortage of workers as this transition hits. So that means it's going to be even more important than ever to actually make this retraining thing work. So that anybody that's involved in MOOCs and online education, things like that, we've really got to make this work this time through. Because essentially, we're going to be in a very difficult situation. And one of the things I want to highlight is just some societies, some countries, particularly Greece and Spain are examples, have like this double whammy because they've got youth unemployment today, even though if you look at their demographics, you can see that the youth that are unemployed today are going to have to be the most productive generation ever, if only to just keep the lights on, right, in those societies. So this is sort of the optimist side is, the pessimist side is AI, machine learning is going to take away a lot of jobs. The optimist side is, gee, if we didn't have this technology coming down the pipe, if we didn't have this ability to dramatically increase productivity, we would be sitting here having conferences saying, how are we going to keep the lights on? How are we possibly going to keep our industrialized societies going in this worker shortage that we foresee in the future? So there's, I think an important need to focus on what are going to be the important jobs for humans to do in the future, what are the worthwhile jobs, what are the meaningful jobs, and how do we make sure that we equip people with the skills and tools that they're going to need going into that future. Now, there's a couple other aspects of this, just to take this, from economics and demographics 101 to 201. One is what typically happens, I talked about workers getting displaced. Those that do find jobs tend to move from the high productivity sectors, the place where productivity growth was high, and therefore, on at least a temporary basis, jobs got removed because of productivity growth being high. They move into low productivity sectors, which, by the way, are also low paying sectors. So more jobs in the low productivity areas, but they're low paying. And this is something that I think we really have to do differently this time. Again, if you imagine that there's actually a shortage of workers, we've got to figure out how to make some of these other sectors higher productivity. So it suggests that trying to figure out how to use AI and ML, not just to improve tech, not just to improve, sort of consumer goods, but also to improve areas like government, healthcare, and education. These are areas that traditionally have been low on the productivity growth curve. This time around, we've got to really figure out how to make productivity growth strong in those areas. So I'm not particularly here with the answers, and I was going to say some words. Again, we lost some time, so I'm going to leave words off about income redistribution and wealth recirculation, and simply say, here are some of the challenges. I'm an optimist, but I want to encourage folks to go out and take on these challenges One is doing a much better job of what the economists call search. This isn't Google search, but what economists think of search, which is matching and equipping people with the skills and matching people to opportunities. We need to do a great job of that. We need to reinvent education, healthcare, and government and really take advantage of these new technologies to increase productivity in those sectors in particular. And we do need to think not so much about wealth redistribution necessarily, but about wealth circulation. Right? I have an unlimited optimism that folks like you will invent all sorts of new stuff that people will want. Right? And what makes our economy go around is making sure that people essentially have enough of a share of the wealth that they can go buy that new stuff. Right? If all the wealth kind of gets piled up in savings somewhere, then that engine doesn't, that flywheel doesn't keep going around. So these are some of the challenges that we have in the economic side. Now, I do want, this is meant to be the tech track, so I do want to switch into the tech side of things and now talk about these concerns about AI that are, again, you can see these are some headlines from the press, but I think there's two types of concerns. One is that the benefits of AI and ML are getting, super concentrated in just a couple companies. And I'd actually expand that to say that those companies are actually using it in fairly narrow ways. In other words, we're making stellar progress, and I do love the progress we're making on things like machine translation, voice recognition, and video recognition, those cat photo things. They are cool, and we're making stellar progress on those. But what we're not doing, and I think Carlos sort of indicated this too, is spreading the benefits and spreading the use, democratizing the use of AI across a wide range of industries. At VMware, we care about that a lot because our customers are basically, all the enterprises in the world. Pretty much everybody buys from us. And so that wide range of customers has to figure out how to use AI and ML. So we want to think about how to democratize these technologies. And the other thing, as I said, is we've got to figure out how to get for us as engineers and developers, get a better understanding of how these systems are working, right? So the thing people don't talk about a lot is for some of these systems, particularly the ones based on deep learning, we really don't understand how they work today. And we've got to kind of admit that, and fix it. We either have to develop an understanding of those technologies or we have to develop other technologies that are competitive with them or better, that we understand better, and that can explain their decisions to people. A place where I disagree with Carlos is I don't think it's as simple as making sure that the data isn't biased. You also have to understand how the systems work. So, as I indicated, we, particularly at VMware, we think about the 99% of all the other companies. You've got a couple hyperscaler companies. They're doing a great job of using AI and ML. How do we spread those benefits? And what do those other companies actually need? Because, I'd argue that they actually need somewhat different AI and machine learning technologies than the hyperscalers do for their needs. So, when I think about this, I sort of distinguish between generic and differentiated machine learning. So by generic, I mean things like, speech, vision, et cetera. Essentially, every company is going to incorporate that sort of technology into what they do. And in many cases, those technologies, the bigger your data sets, the bigger your training data set, the better your technology is going to work. So a small number of companies are going to collect very large data sets and deliver up great image recognition, for example. And you already see this with Google and Microsoft in particular doing a great job on this. And as I said, it is very cool technology. So that's really good. From the point of view of Google and Microsoft now, they're differentiated from their competitors. But what about a company out there? If you think about a company that's out in just about any industry, I'm company A, I get my stuff from Google. Company B gets the same stuff from Google. So this doesn't actually help us compete with each other. It's not differentiated, right? So although these are great technologies from the point of view of the companies that are out there competing with each other in the marketplace, these are actually quite generic. What will allow companies to differentiate themselves from each other is how they use the data that they have and their own domain knowledge of the domain that they operate in to essentially gain competitive advantage. So a lot of what we're interested in is not the hyperscaler AI ML. As I said, it's very cool, but how do we get this into the use by lots of other companies so that they can apply their domain knowledge and their data to problems of interest to their industry? So we work with sort of our own researchers, but we also work with university partners. Carlos mentioned the folks at UW. We work with folks Berkeley, Stanford. One project that's really caught my eye on this, if anything, because of the commitment to what I think of as this important space, is the Project Dawn at Stanford. You'll recognize some of the folks in there. Matei, when he was a graduate student, the one that kind of brought us things like Spark and Mesos. So they have a pretty good track record. He's moved over from, he was a grad student at Berkeley, now he's a faculty member at Stanford. And I'm just going to let Peter Bayless there describe a little bit about what they're after, but I think the key thing is they're really trying to, again, make machine learning much more accessible to people in many other companies. We'll see if the audio works.
Machine learning applications are developed by large, expensive teams of very well-trained individuals.
Audio guy here, or is he left?
Because it's so expensive to construct these applications, we find that ML is only applied in a small fraction of the domains in which it could be deployed and developed.
Hold on. Well, first we'll get the audio pumped up.
More accessible to a wide variety of users. We have large...
Let's go, Peter.
Today's machine learning applications are developed by large, expensive teams of very well-trained individuals. And as a result, because it's so expensive to construct these applications, we find that ML is only applied in a small fraction of the domains in which it could be deployed and developed. The goal of Dawn is to make machine learning application development easier and cheaper, and therefore more accessible to a wide variety of users. We have large amounts of data. We want to extract value from this, but because we lack reusable systems and tools for automating some of the most tedious and expensive parts of the machine learning application development, essentially we see ML deployed in a much smaller set of domains we think could be possible.
Okay, so that's an example. There are various other groups we've been sort of working with, trying to get them working to spread these tools out, make them more available. This is the Dawn stack that the folks at Stanford are working on. As I said, the folks at Berkeley are working on a different stack. You heard about work at UW. So I think some of this is going to help make these tools more available. I think there's also questions of the balance when you go to use AI tools. Realistically, one of the first things that has to happen is a human data analyst has to go look at the data and say, okay, I've got this data. How am I collecting it? Is there any signal in here, or is this just all noise? Where is the signal? Do I need to clean up the data? How do I need to clean up the data? Because probably there's going to be various types of errors that have crept into the data. They're going to be idiosyncratic, and you're going to have to sort of spot those and clean those out, or change your collection techniques. What type of machine learning model should I be using, right? So that's a high-level decision that needs to be made. So there's a bunch of those human things that need to be done, and once you've done those human things, then you can unleash this machine learning model. So the difference is at the hyperscalers, you sort of do a bit of that human stuff, and then you run, enormous amounts of data through the system. In the typical enterprise, as Carlos indicated, it won't be the massive, it'll be huge amounts, but not massive amounts. I think he said massive is bigger than huge, I guess. And I think he's hit that correctly. So what you're going to have is a higher balance. In other words, the human part is going to actually consume proportionally more resource. So within VMware, we've been trying to dedicate some of our research expertise to seeing, can we help with tools for the data analyst? So I'm going to show a clip here from a research prototype we've developed that's intended for that, to help the analysts dip into some new data that they found. In this particular example, it's going to be an FAA data set. That is basically all the flights in the US over, I think it's about the past 20 years. So it's a decent sized data set. The tool itself, by the way, is designed to deal with literally billions of rows with thousands of columns. So think of these as just enormous spreadsheets. But this one will just be running with, I think it's hundreds of thousands of rows.
The data set, you could think of it as a huge table which has 15 columns shown here, day of the week, flight date, unique carrier, and so on, and has 124 million rows. You can actually choose a specific column, and then what you can do, you can plot the data as a histogram. On this histogram, the x-axis is the departure time, and for each time, we have a bar showing the number of flights. Now, for this histogram, because we know there are 24 hours in a day, the best way to display this data is actually to bin it using 24 bins. And then the blue line is the cumulative distribution function. It shows you for each point how many flights, what percentage of the flights occurred before that point. Now, if you look at this blue line, it kind of has a funny shape. It zigzags up and horizontally. You wouldn't expect this pattern. So we can see what happens by zooming into the data. For example, we'll choose the interval between 8 and 10. Now, if you look at this data, we can see there's a lot of flights between 8 and 8:59, and there are no flights between 8:60 and 9. So the reason for this funny shape is the fact that this database encodes the departure time as an integer instead of using date time. This is exactly what this tool is about. It's about finding anomalies in your data.
So, again, there's a whole bunch of, fancy techniques that go into giving you a visualization into these enormous data sets and doing it in real time. So there's a sort of whole, kind of distributed system behind that. I won't go into the details, but happy to talk about them with folks later in the day. The main thing, though, is finding ways to help those human analysts dip into the data very quickly, figure out what's going on, what needs to be cleaned, what model to be used, and move forward. Now, another aspect of differentiated machine learning, again, what the 99% of enterprises that aren't hyperscalers are going to need is to focus on other types of machine learning problems like anomaly detection. This is a really common type of problem. You're trying to find anomalies in data sets. If you find anomalies, you can use them for alerts, you can use them for root cause analysis, for security. We use this for intrusion detection. And the catch here is that you're often interested in anomalies that have to do with something going wrong across multiple dimensions. And let me just sort of try to do a real simple version of this. Here's a simple case: is if I just am tracking one metric over time, right, then it's kind of easy for me to spot an anomaly. I notice that the thing goes up and down, and then over in the third time something's going a little funny there, right? So it's not following the traditional pattern. Okay, that's just data that's essentially one metric plus time. So one dimension plus time, sort of two dimensions. If I start having two metrics, in this case we're just plotting the metrics against each other, x versus y. We just left the time dimension out of here, but assume each dot is a sample in time. You can sort of see that the outlier here is a perfectly valid y value. Like if we were up around t equals 30, or x equals 30, that would be a good y value. But at the point where it's occurring, it's the x versus y is not correlating. Right, so that's another type of outlier that we could look for, 2 dimensions. And again, we do this over time, so it's really 3 dimensions in total. The catch is when you try to do this in tens of dimensions, you can't just plot it like that. It gets very hard, not just to visualize, but actually hard to compute. There's a gold standard for doing this, a really good algorithm called PCA, Principal Component Analysis. It's been around for a while. And it allows us to generate anomaly scores for multidimensional data. So you can look at data that's across many dimensions, or think of it as you've got many metrics, and you want to notice when sort of multiple things are going on, right? The nice thing about PCA is we understand why it works, right? So that's an important aspect. Just really briefly, quick tutorial on PCA, and I know I'm running out of time here, is you basically, this is just showing 3 dimensions, but imagine you have the data's coming across many dimensions, right? So you're plotting points in space, many dimensional, and what you're going to do is choose a 2-dimensional plane you'll call the principal subspace. Let's say it's 2-dimensional, okay? And when a new data point comes along, there's our data point in blue, you're going to actually just project that data point down onto the plane, onto the simple 2-dimensional plane, and you're going to basically use that to come up with 2 scores. One is the projection distance. How far out of the plane was this data point? If it's an anomaly, it's going to be really far out of the plane because we chose this subspace to sort of capture most of the stuff, to be close to most of the stuff. So how far out of the plane is it? And then what's called a sort of leverage score, which is sort of the where it lands, in terms of its projection on the space. So on the plane that we were trying to, look for anomalies, we have a place where we expect things to be. It's a Gaussian distribution. If things are far away on that distribution, that's also a symptom of an anomaly. So PCA lets us take these multidimensional things, squash them down, get a few results. So the great thing about it is we understand why it works, mathematically understood. The bad thing is that the algorithm scales quadratically. So it's, okay, we can do it with tens of dimensions, maybe with hundreds of metrics, but if you're doing things like, again, intrusion detection or measuring sort of spurts on VMs like we do, you've got large numbers of metrics, large numbers of dimensions. So the challenge we had for our researchers is, can we sort of get PCA to work, but with many, many, many more dimensions? And the simple answer is yes. We can do that by essentially applying some randomization to essentially kind of a random sample. So different times we get samples, we will use different combinations of the metrics. We'll combine that. That'll give us a way to, it's called a system called matrix sketching. And the important sort of bit of progress here is, well, we know matrix sketching is cheaper to compute than PCA, and we knew that it preserved some of the geometric properties. So by preserving geometric properties, imagine if you have similar, remember, take you back to sort of grade school geometry, if you have similar triangles, they preserve the angles. So we know that when we do this squashing down, we're able to preserve some of the properties. The new result is that you can actually also preserve higher order geometric properties, and particularly those projection and leverage scores. So the net result of this is we can speed up anomaly detection, and we know how it works, right? You don't have to understand all the details, but it says we can now speed up anomaly detection. We know how it works. Because of our problems before, I'm now running out of time. So I just want to come back to really briefly this explainable AI thing. And Carlos touched on it. I think it's a really important challenge. DARPA's taking on this challenge somewhat. I had a video here from my colleague Dave Gunning. I'm going to set this aside and not play the video, but ask you to, if you're interested, take a look at what he's doing in his XAI program. So make sure the video skips. But the key thing here is, I'm saying as a field, I think we should not be so pleased with our great progress with deep learning, because we need to realize that it's important, we have a compact as engineers with society that we understand how the technology that we foist on the world is working. And that says that we either have to figure out how we're going to constrain deep learning, so we're going to be able to give people assurances that even if we don't understand exactly what's going inside the black box, we've constrained the outputs of the system as a whole to be able to make guarantees and assurances that the system as a whole never deviates outside of the safe areas that have been defined, right? If you get these inputs, I guarantee you the outputs will stay in the space. That's one approach we can take. We're looking at that. We can get a better understanding of deep learning. That's definitely an approach we're taking, and I think some of the really interesting work there are things like people going and taking deep learning networks, pruning them to try to remove the inside nodes that don't contribute significantly to the results. Now you've got a simpler model. Maybe the structure of that model will tell us something about how deep learning is actually working. And of course, we should be on the lookout for alternatives to deep learning. So I'm going to, pretty much wrap it up there, and basically say key challenges in this part of the talk. Democratize the use of AI and ML. Let's get it out so all the enterprises in the world can use it. Let's get a bigger focus on the things that will help those companies differentiate their stuff from each other, and increase the transparency and the explainability of machine learning decision making. So finally, just want to tell you, I'm optimistic about all this. These are challenges we need to confront. You're probably going to hear more about them during the day. And there's lots of optimists out there. So please choose optimism.